Good morning, everybody. So today we're going to talk about eigenvalues and eigenvectors, start of a new chapter here for us. This is page 92 of the workbook that we're looking at. And eigenvalues and eigenvectors have a number of applications that we're going to explore in this chapter. One of which is that they help us to come up with nice representations of linear transformations in terms of matrices. Okay, so let's look at the definition together. You might find that this is partially familiar to you from Math 241. Okay, so we're going to start with a linear operator, and I don't know that we've used that word in this course yet. Operator just means that it's a linear transformation that goes from a vector space to itself. In other words, the domain and the codomain are the same. Okay, and then we come to the definition of an eigenvector. So what is an eigenvector? It is a non-zero vector in our vector space such that if you plug it into the linear transformation, the following statement is true. T of v is equal to lambda of v. In other words, an eigenvector is special in the sense that when you plug it into your transformation, you get a scalar multiple, lambda times v, back again. Okay, and if this happens, we call that scalar an eigenvalue that's corresponding to the eigenvector. Okay, and down below, you can make the same sort of definition for an n by n matrix. Okay, there, an eigenvector is just a vector that's special in the sense that if you multiply your matrix by that vector, you get a constant multiple of the vector back again. Exactly the same definition as you saw above for a linear operator. Okay, so what we'd like to do is to first explore this definition graphically a little bit. Okay, so in example 1, we will start with a matrix, just a 2 by 2, and we're going to take a few vectors and left multiply this matrix by the vectors and just see what the behavior is. What comes out? Do these vectors look like they might be eigenvectors? Okay, so we'll start with the vector 2, 1. Okay, they're asking us to take a times v. Let's maybe do that calculation up here. So we're going to take our matrix and multiply it by that vector 2, 1. Okay, just do the multiplication and see what we get here. So let's see, 2 times 5 is 10 minus 6 is 4 in the first coordinate, and then 6 minus 4 is 2 in the second, and so we get 4, 2. Okay, and let's go ahead and just plot those vectors together. So 2, 1 looks like that. There's v. And AV is 4, 2. Okay, so let me switch colors here. So 4, 2 would go to here. All right, so there's v and AV for the first example. Okay, let's do that same experiment over here for v equals 3, 2. Same calculation for AV. Let's see if we can maybe sneak that in up here above again. 5, negative 6, 3, negative 4, this time times 3, 2. Okay, and you can do the arithmetic here, and we're going to get 15 minus 12 is 3, and 9 minus 8 is 1. So we're going to get 3, 1 out of that. Okay, and if you plot the two vectors this time, let's see. 3, 2 looks like this, so there's v. Okay, and then 3, 1 is just down here a little bit farther. There's AV. Okay, and finally, I'm going to trust that you could do this last calculation on your own. Same idea, we're going to take 3, 3, multiply a by it. This time we're going to get negative 3, 3, which you can confirm. Okay, and we'll go ahead and plot those two vectors. So 3, 3 looks like that, and then AV is negative 3, negative 3. Okay, points in exactly the opposite direction. Okay, and so we come to the question then in part B here, and I'm just going to scroll us up a little bit. Are any of the vectors v from part A eigenvectors of A? Okay, well, let's recall together what the definition of an eigenvector was. Okay, that was a vector that was special in the sense that if we multiply a by that vector, we get a constant multiple of the vector. Okay, so if we look back up at part A here for the first vector, 2, 1, we're simply asking, when we took a and multiplied it by v, did we get a constant multiple of the vector that we started with? And you can see that we did. We started with 2, 1, and 4, 2 is exactly twice it. Okay, we can confirm that down below by direct calculation. We started with v1, we took a times 2, 1, and we got out 4, 2, which is exactly twice 2, 1. Okay, and the eigenvalue in this calculation would just be lambda equals 2. That was the multiple of the starting vector that our output gave us, basically. Okay, now let's move over to the center vector, 3, 2. Is that an eigenvector of the matrix A? Okay, well, in this case, the answer is no, because we can look at the vector that came out, 3, 1, and it's not a multiple of 3, 2. Okay, it doesn't fit. And you can see that in the picture down here as well. AV is not a scalar multiple of V. Okay, it's pointing in an entirely different direction. Okay, so 3, 2 is not an eigenvector. What about the last one? 3, 3. Same question. Is -3, -3 a scalar multiple of the vector that we started with? Okay, and in this case it is. It's just a negative scalar multiple. So we started with a vector v and ended up multiplying it by -1. Okay, so just to confirm algebraically that 3, 3 really is an eigenvector. Okay, we're going to remind ourselves that when we took a and multiplied it by 3, 3, what came out for us was -3, -3, which is -1 times the vector that we started with. Okay, so for the vector 3, 3, we got an eigenvalue of